Welcome to qnawire.
Um, in this case, in the new problem, we have two cases. We have two cases. In the first case, we have a spring that's being stretched. And then in the second case, we have a spring that's being compressed. The forces involved are variable, and the spring doesn't always obey Hooke's law. So if you have the spring right here, the initial position x naught, it's being stretched a distance of 0.050 meters. Okay, and in the second case, you have the initial position of the spring, but it's being compressed this direction by a distance of negative 0.050 meters. So those are the two cases. The force involved in the compression and stretching happens to be kx bx squared plus cx cubed. It's a variable force. The constants that are given, k is given as 100 Newton meters, b is given as 700 Newton meter squared, and then c is given as 12,000 Newton meter cubed. So one of the things that happens is we're being told in terms of stretching that when x is 0, the spring is stretched, and then when x is 6, so when x is less than 0, it's stretched, and then when x is 6, it's when x is greater than 0, it's compressed. Okay, so those are just some of the details that we get. We want to find out the work involved in part A. What's the work in stretching the spring? What's the work involved in stretching the spring? This is a variable force, so it means that we're going to use an integral from the initial position x0 up until the final position of 0.050, that's in stretching meters. This involves the force, and the reason why we're doing that is, remember, if you want to find the work involved, it's the same as the integral of the force times dx, force in x times dx. So that's what we're using to find the work involved in stretching the spring. Remember, if you have an integral, you're thinking about the area under a graph. And so the x-axis is the force, the y-axis is the displacement, whatever graph you're dealing with. Each infinitesimal slit on the graph will be dx. So this is finding work is the same as finding the area under the graph, and that's what we're doing in this problem. So kx minus bx squared plus cx cubed with respect to dx, that's the integral we're looking for. When we do the integral, remember a simple integral, if you have x to the n, then to do the integral of that is x to n plus 1 and n plus 1. And so if you have x raised to 1, then the integral will be x squared over 2. And that's what we're doing in this problem. So we do k is a constant, x squared over 2, minus b is a constant, x cubed over 3, plus c is a constant, x to the 4 over 4. The limits are from 0, x0 is 0, up until 0.050 meters. And then we plug in the numbers. Remember, k happens to be 100 Newton over meters times x squared, which is, when you plug that in, you get 0.050 meters. That squared, minus b happens to be 700 newtons per meter squared, and then you multiply that by x cubed. X is again 0.050 meter cubed. This is now a cubic function with the b. and this is over 3, remember. And then the last part is C, which is 12,000 Newton over meter cubed. I think we have to change this. Well, this is fine. We have to multiply that x to the 4th power, which is 0.050 meters, all over 4, but this one is raised to 4, and so this is over 4. That's the initial part of our integral, and we're going to subtract 0 in the second part of the integral, and the reason for that is for the lower limit of integration, if you plug in 0 for all of these, you're going to end up with 0 in the expansion. So when you simplify these values, and this is going to be equivalent to 0.173 joules when you simplify these values. And that's the final answer. So once again, if you're stretching the spring, your limits are going from 0 up until 0.050. We're using the work integral formula. Remember, work is force times distance, but if the force is variable, you think of it in terms of the area under a graph, so you're getting the integral of that. Each infinitesimal slice is dx, so when you get the integral and the limits of integration, because you're stretching from this point 0 up until this point 0.05, and that gives you energy of 0.173. Actually, it's not 173. I need to take that back again. If I plug in the numbers, I get so 100. This is 100.5 over 2. This is 0.05 over 2 because of this 2 right here, and then negative 700 Newton meters squared over 3. That's fine. And then plus 12,000 Newton meters squared over 4. That's fine. So when you simplify that, you end up with 0.1146 joules. Okay, 0.1146 joules. And that's the work when you stretch it. In the next page, we're going to talk about the work done when you compress it. So again, you start at x0 and up until the point of compression, which is negative 0.050 meters, and you still have the force itself, and that happens to be kx minus bx squared plus cx cubed dx. And the reason why we're doing that is because work is seen as an integral. Okay, the area under the graph, fx dx. So if you have a graph again, you're finding the area under the graph. This is the infinitesimal dx. So we're going to do the integral of that. So this is kx squared over 2 minus bx cubed over 3 plus cx to the 4th power over 4. The limits of integration from 0 to negative 0.050. We do have the values of k. If you go back, you see that k is 100 Newton per meter. So we're going to plug in that times negative 0.050 meters. We have to square that over 2, and then minus, we go back, you see b is 700 Newton meter squared. So we write that 700 Newton over meter squared, and then we plug in the negative 0.05 meters. That's cubed over 3 plus c is 12,000 Newton per meter cubed. 12,000 Newton per meter cubed. Again, you plug in negative 0.050. It's a little bit tedious, but you just want to be patient over 4. That's the first part of the integral. And then the next part we're going to subtract 0, and the reason for that is if you plug in this 0, the lower limit, into that variable, those three variables, you're going to get a final answer of 0. If you simplify that problem with the minus, you end up getting, you can use your calculator, you end up getting 0.173 joules. So if you compare these two, you can see that there's more work required. So compression requires more work than stretching. And you could try this at home. If you're trying to stretch something and then you try and compress something, they did mention that the springs don't always follow Hooke's law perfectly. Even in that case, still you will find that it's easier to stretch than to compress. So thank you very much once again. Feel free to send me comments or questions on the spring constant, the energy involved in the spring. Remember, Hooke's law always plays a role, but the big deal about this problem is the integral, because we have a variable force. If it's a constant force, you don't have to worry about the integral for the force times the displacement. Okay, bye-bye. Have a wonderful day.